Here is a mini lecture, Introduction to Surfaces. So we're now into section 8, which is about the genus of a knot, and I'm going to tell you what a surface is. And so this is what you can read in section 8.1, but actually that's a little inaccurate. Really, you can read about this on pages 48 to 49. And you only really need to look at the top bit of 49. Okay, so by the way, this is going to be a little vague. We're not going to go into the full theory of surfaces and so on. Okay, so what is a surface? It is a bounded two-dimensional object. Okay, that's a bit vague. Actually, it's a topological space with the property that every point of your topological space has an open neighborhood homomorphic to R2. So it's a space that's locally homeomorphic to the plane. And in our case, they're always going to be compact. So that's what I was talking about there with the brackets. If you don't like the sound of that, then feel free not to think about it too much. Okay, so here are some examples of surfaces. On the far left, we have the sphere. This is the surface of a ball. Next, we have the torus. This is the surface of a donut. So it's like an inner tube, if you like. And then here we've got a surface of genus 2. This is a bit like what you would get if you took a couple of tori, chopped a bit off one of them to make a hole, chopped a bit off another one to make a hole, and then glued them up to form a single solid there. So that's what the surface of genus 2 is. Again, it's just a surface. If you filled it in, then you would get some kind of donut with two holes. Next, continuing, we have the disk. So this is the set of all vectors in the plane of length 1 or less. In particular, these points around the edge, I'm including them. And I've shaded it in to sort of show you that it's flat and living in the plane. The first three cannot live in the plane. The next one is the annulus. Annulus, of course, means ring, and that's what it is. It's a disk with a sort of little disk in the middle chopped out. And finally, we have the Möbius strip. So if you wanted to make this physically, you would take a strip of paper and glue it round to make a loop, except you would insert a single half twist before gluing. Okay, so these are our example surfaces. Now, a surface is called closed if it has no boundary, and it's not called closed if it has a boundary. So which of these have boundary and which don't? Well, these do not have any kind of boundary. They are closed. While these all have boundary. What are their boundaries? Well, whoops, that's not what I meant to do. For example, with the annulus, what's its boundary? Well, this isn't going to work. It's the union of two circles, right? It's this circle in the middle. Let me highlight the boundary. It's this circle in the middle, disjoint union, this circle around the edge. That is the boundary of the annulus. It's two circles. What is the boundary of the disk? It's a single circle around the edge there. And what is the boundary of the Möbius strip? Well, let's see. It's this. Let's keep going. This, under and then back round, this. So it is another circle, but it's twisted up in a slightly different way than with the other examples. And we're normally going to look at connected surfaces. That's ones you can't write as a union of two other surfaces. Okay, the next thing we need to know about is orientations. An orientation of a surface is a choice of clockwise at each point. So you see, if you look at a clock, then you know what you mean by clockwise. But imagine the face of your clock was transparent and the numbers were written on this transparent surface. Then you could look at the clock from the other side. Well, the numbers would be backwards, and also, which way would the clock be going? Anti-clockwise. So what that's telling you is that your choice of clockwise on your clock would change if you looked at it from the other side. Now, with our surfaces, I haven't told you that they have fronts and backs or insides and outsides yet. And so you can look at them from both sides, in which case, which is clockwise? You don't know. Well, an orientation is simply a decision. You say what clockwise is at each point. So we could do that, we can do that with the disk by letting clockwise at each point be clockwise in the picture, right? So here is an orientation of the disk. And the rule is that these different choices of clockwise have to match up as you move around. And indeed, if I picked up this one here and dragged it over there, I'd get the one that I've already drawn over there. You could do that with the torus as well. How would you do it? Well, what you do is at any point, you can draw the outward pointing vector that points out from the inside, like that. So that's coming out of the surface. And then at that point, I can draw in a right-handed screw. What's that? Imagine the arrow was a screwdriver, this was its point, then which direction would you have to turn it to tighten the screw? That's what I'm doing there. So let's just leave that as it was. Okay, that's an orientation of the torus. And what about the Möbius strip? Well, how about I give myself an orientation here? Well, then my orientations elsewhere, they have to be consistent with it. So if I took it and dragged it round over to near this kind of twist, then it would look like this. So that's if I pull it that way. If I did the same thing going this way, then I'd get this. Actually, let's just move that back a little bit. If I moved it this way, then I'd get this. But what happens if I take this and pull it through the twist and come out the other side? Well, it'll have been rotated through space 180 degrees so that as we look at it, it'll be going the other way. And now what we see is that actually our orientations do not match up. That's because these two are going in the opposite directions and they're neighbours to one another. So these do not match. And in fact, what we've just demonstrated is that the Möbius strip is not, the Möbius strip has no orientations. Okay, so the definition is that a surface is orientable if it admits an orientation. So what we've seen is that the torus is orientable. And we've seen that the disk is orientable. And we've seen that the Möbius strip is not orientable. Okay, so that's our introduction to surfaces and orientations and so on.